I'm going to talk a little bit about what we've learned over the last 15 years on an English chalk stream about juvenile migration. We've heard a lot about marine migration in the previous session, and Colin touched a bit about the potential perils of smolts when they go down the river. The thing with these Atlantic salmon is that, of course, they have a split life cycle, if you like, and they need to get from their freshwater juvenile area into the sea. And that can be quite a dangerous journey, and there's quite an increasing amount of literature coming out in the last decade, I suppose, highlighting how dangerous this journey can be and what a large proportion of these fish we're losing in some places in particular. So I'm going to talk to you about that, and I'm going to talk to you about the 15 years of experience that we've had on a chalk stream. You see a picture here. It looks a bit different to an Icelandic river, but essentially in the south of England, where this work is based, and despite it looking different, the fish species is the same and takes a lot of the same cues from the environment, I'm sure. So we've heard a lot about acoustic tagging and a little bit about satellite tags here in the last session. We're now going to go to a slightly different technology, which is 2 or 3 orders of magnitude cheaper, which enables us to look at a lot of individuals, so big sample size. So I'm going to talk about over 20,000 observations of individual juvenile salmon here now. And how are we doing that on the River Froome? Yeah. Annually, we go out and electrofish large parts of the catchment. You see the catchment here, and in the red circle is the area where we electrofish large parts of. And we do that in September time. And we do that to mark 10,000 juvenile salmon every year, and that's about 10% of the population at this stage in the catchment. And the identifier is a pit tag. These are known to dog owners, etc., as microchip that the vet puts in the shoulder of your dog. The same technology. They don't carry a battery. They'll stay with the fish at least until it's first spawning. So we learn a lot about it from these. They don't have a battery, so there's no battery that expires. These things are important to remember. So we go out and pop one of these into 10,000 juvenile salmon every year. And then we monitor the migration of these and the movement of these fish subsequently using stationary recording stations. And here's the catchment. You'll see there's 4 sites where we have full cover of these pit tag antennae, and the one I'm going to focus on today is the most downstream one, which is down at East Stoke. And important knowledge is that this is about 8 kilometers from the tidal limit of the river. So there's a bit of river downstream of us, but we're going to focus on our most downstream point in terms of observations. And important point here is that these antennae, they run 365 days a year. So it's continuous monitoring. And we're not dipping in and out as you traditionally would if you're trying to sample a population. And this is hands-on off once we've tagged these individuals. Right, what have we seen? What I've done here is I've plotted these sort of 15 years worth of detections of juveniles at East Stoke. And you can see here that over the years, very nice spring smolt peak is showing, classic spring smolt. But early on already when we started this tagging word was that early observation was that we saw a substantial number of juvenile salmon migrate downstream in the autumn. And this came as a bit of a surprise, really, to the group. But, so important to understand better what component this is and how they fare, etc. So what are they? Well, they are fish that migrate at discharge events, where you see here, this is just one antenna in a particular year, but it sort of nicely highlights the green line showing the discharge in the river and the bars indicating number of tags detected. And you clearly see the first handful of discharge events in the autumn, they are associated with this downstream migration of juvenile salmon. And once we're past the first sort of handful discharge events, you can get subsequent discharge events and they don't really trigger any further migration. So these individuals, they move on the first handful of migrations. Another very interesting observation regarding these fish is that they migrate at night time here. I'm showing you the number of detections. It's about I don't know, 7,000 detections or something like that here. And you can see that over 90% of them actually move at night time. And that's important. And why is that important? Is because there was sort of a theory when people first realized there were fish moving, juveniles moving in the autumn. They thought, well, maybe these fish, they just get pushed out by these high flow events. But the fact that they don't move during the day sort of illustrates that this is an active decision to be moved downstream, if you like, because why would it not happen at daytime at the same rate otherwise? One of the first questions then was really, is this an early migration to sea? Are these fish going straight into the sea and not following the textbook and entering salt water in the spring? And the group at the time did various things to try and look at that. And one of the things that we know is that sodium, potassium, ATPase activity over the gills is one of the main ways that salmonids regulate salt water. So they need to have a high level of this to be able to tolerate salt water. And what you see on the bar graph here is the white, the electrophished rivers of resident par in the autumn, and the first grey one is fish that were migrating. There were similar levels of this ATPase and much lower levels than the actual spring smolt. And the group then also did put some of these autumn migrants to the test with salt water, and sadly they didn't make it. So no, they're not ready for salt water. They have to stay in fresh water. Another theory was that these were subordinate individuals that got pushed out by dominating individuals. And we had a look at that, and we looked at the time of tagging in September. Was there any size difference between the fish that we observed migrating in the autumn and the ones we observed migrating in the spring? So remember, these are measures taken at the time of tagging in September. And no, they were the same length and they were the same weight. There was no difference. The fish that were definitely smaller were the ones that we never saw against, essentially the runts. They just didn't make it. But no, there wasn't any evidence to show that these are not healthy individuals and they're subordinate and getting pushed out by dominant individuals. What we have subsequently also observed is that we've observed a number of these fish coming back, and over about I think it's roughly 7,000 of these autumn migrants we've clocked over the years, and 0.6% of them we've detected coming back to the river. Less than 1% doesn't seem much, and it is a lower percentage than our spring smolts. But one thing you need to keep in mind here is that of the ones that leave a spring smolt in the river Froome, more than 50% of those individuals actually die in the period between being tagged and the next spring. So we have a very high overwinter mortality in the river, and that's not taken into account here essentially. So we probably have very similar marine survival of these autumn migrants than we do of the spring fish. Right, interesting fish, and I'll put a few more points to them at the end. But let's move to the spring smolts. This nice distribution you see here for the last 15 years. And I think there's the 16,000 individuals you're seeing plotted there. 6 weeks is the sort of smolt run period on the River Froome over the years. But let's have a look at what triggers them to go and when are they ready. What behavior do we observe when they're moving down the system? So we've done a number of analysis of that, and I'm just going to jump into one of the more recent ones here, where we actually did a sort of large model looking at what dictates this. Now, one of the things that we've observed over the years is that smolt size decreases as the season goes on. So essentially, the take-home message is that the bigger smolts, they leave early. Another point that has proven to be very important for when they leave is the temperature. We've got to remember these are cold-blooded animals. Their development, their physiological development depends on temperature. And therefore, when you see here in this plot here, the blue points shows that the variation of the middle fish, so the median fish, when are we halfway through the smolt run on the River Froome? And you see over those years that there's quite a bit of variation among the blue dots. But if we then take a look at the cumulative temperature in the spring, so from late winter until we are halfway through the run, what's the cumulative temperature? We call that degree days, and you see that's very stable. It looks like from 1st of February, these fish, they need about 750 degree days to reach the middle of the smolt run. So clearly, temperature dictates when the overall timing of the smolt run, and that also came through as a very strong effect in our statistical model. And the observant person earlier would have noticed that there was a decline, or it looked like they were getting earlier, and that is very, very clearly the trend that over the 15 years we've been monitoring these smolts, that we are roughly a week earlier now when we're halfway through the smolt run than we were in 2006 when we started this. So these fish are moving earlier. That's causing some concern because the fact that they experience higher temperatures and the river is developing earlier in the spring, if you like, with climate change, means that they're ready to go earlier. But the good conditions don't necessarily develop at the same rate at sea, so we risk potentially having this mismatch of conditions telling the smolts in the river that now is the time to go to reach the optimum temperature conditions at sea, but that might not actually be the rate that the sea has developed at because it's obviously a different beast in terms of thermal capacity. Now I'm just going to briefly mention some of the other things that we found that really dictates this. RCT, relative change in temperature and relative change in discharge. So essentially they're positively related to when these fish relieve. So when we have an increase in temperature and an increase in discharge, that makes these fish move. That makes the smolt go to sea. And interestingly, when we looked at it in a slight more detail than I'm going to present here, is that actually that even within the smolt run, that they have different effects. Increases in temperature is particularly important at the beginning of the run, triggers them going, and gets very important again towards the end, essentially telling them you must go now, I suppose is the message. And the discharge is also very, very important towards the end when the fish essentially physiologically are ready. If they then get a trigger from an increased discharge, they really go. Moon phase, yes, a bright big full moon, no, they don't like that. They prefer nice dark nights. I understand during the smolt run up here in Iceland you might not have dark nights, but we do endorse it in the south of England. And actually where the position of the individuals in the system also came out is quite important. So the individuals that were tagged lower in the system were also the individuals that we observed first. So they went to sea earlier. Another interesting observation in the model is that the fish school up, but that they do that particularly at daytime. Not so much at nighttime, there's no evidence of that. And I've just plotted a little plot here from an earlier paper that nicely illustrates this. When I say schooling, then I mean fish, two tagged individuals detected within 10 seconds of each other. And on the top plot here in the blue bars, you'll see observations where two individuals were detected within 30 seconds of each other. And you clearly see that nearly all those observations are clumped within, so they observed within 10 seconds of each other. Essentially, these fish, they're traveling together in a school, whereas at nighttime, it's individuals observed within 30 seconds of each other. The distribution is just random. The schools appear to break up at nighttime, but be very important for them during the daytime. Right. Another very interesting observation that we made in terms of the behavior of these smolts when they go to sea is that at the start of the run, they run during the night time. What you have here is date out the x-axis, and up the left-hand y-axis is the ratio of night to day. So essentially, the lower the value, the more dominant, the higher proportion of fish migrate during the night, and the higher you go, the higher proportion of daytime migrants. And what we see there is that towards the end of the smolt run on the River Froome, we start to get a pretty even distribution of nighttime and daytime runners. And this is all associated with the temperature of the water. So essentially what we're finding year on year is when the average daily water temperature reaches 12 degrees, then the fish really start moving during the day, whereas before that they're nearly all during the night. And it seems that it's a cue for them when the temperature gets that high. Well, actually now you just must start thinking about going, and therefore they change their strategy to a more active decision of actually also migrating during the day. Another key observation we made is that there is a particular crepuscular, so essentially depression in the migration. So there is very much a depression in the number of individuals that we see migrating around sunset and sunrise. So when they're running, for example, during the day, we really see that they stop around sunrise and they also stop around sunset. They just don't like to migrate at that time for some reason. And one of the reasons might be that a lot of the visual predators in the system, and here's pike, where we did a study looking at their activity essentially when their feeding bursts were, and you see they're nicely located around sunset and sunrise is where they are most keen to feed, and that goes for a lot of the visual predators. So maybe the smolts just know that that's not a good time to migrate. Maybe they just know we should just hang tight for a couple of hours and wait. Right. Just sort of to sum up a little bit, what have we learned? We've learned an awful lot, I think. But we've learned that for these autumn migrants, and we know that it's not just on the River Froome that you see them. We've seen them in system in Scotland, we've seen them elsewhere. They're just not observed very often because usually when people go out and trap these fish, they go out and trap for the classic spring smolts. And they don't have equipment that monitors this 365 days a year. So, but they're associated with discharge events in the autumn, and only the first handful in the autumn. They're always at nighttime virtually. They're not ready for sea, these fish, and they're not subordinate individuals. So I suppose the state of knowledge really is that that it seems to be an early start to their marine migration, where they'll take a break then over the winter. And it sort of makes sense because in the autumn we always get these dirty waters that makes it difficult for the predators to see the fish, and that's related again to the nighttime stuff. So our knowledge is that we think they make this early start towards sea migration in the autumn because they can do it relatively safely. From a conservation point of view, it's important because these fish, they go and inhabit the lower river, and any salmon ecologist that go and look at the river there, they'll say this is not juvenile salmon and salmon habitat. But actually it is in the winter. There's a lot of them there. And these fish are not unimportant because they do return and contribute to future generations. So we mustn't forget these. Spring smolts. The early spring temperatures really dictate when we see these fish. As for the individuals, the size of them and the distance from sea is also important in terms of when they actually make it to sea. The triggers of migration really relates very much to the increases in temperature and discharge, and that varies throughout the smolt run, how they impact it, but they're key. And the behavior of these smolts in their migration towards sea is also changed by the environment that they migrate through. We've since then taken, so we learned an awful lot about, we know a lot about when do we see these fish migrating in the autumn, we know when they migrate in the smolt run. So we know when is the time to protect them, if we can. But we've also taken that a little bit a step further and looked at in the estuarine environment using a different the acoustic technology, looking at when are they there. So we have, for these systems, a really good handle on what's the time to protect these fish and what's the time to look out for, say, high densities of predators in these environments. I'm going to steal another 30 seconds just to say, we talked a lot about smolt detections here, but of course this technology offers a lot of other things. We can look at which part of the river do we have the highest survival in. So here we see on the River Froome, fish that we tag in the upper part of the catchment, they're just more likely to survive to smolt states than lower in the catchment. And we can also look at subsequent impact of marine survival. The bigger these smolts are when they leave, the more likely we are to see them come back again.